Hello, my name is Ivan Taylor, and I'm from Policy Dynamics in Ontario, Canada. And this is a presentation I gave to the Nigerian chapter of the System Dynamics Society on February 17th, 2023. And this presentation is entitled The Building Blocks of System Dynamics. And I'm going to show how system dynamics works by building two small models of the Nigerian population. So the first model, I will create a new model here in Vensim, and this will be in years, and I'll run it for 100 years. And so I'll write in a stock. A stock is going to be population, and that'll be the accumulation of people over time. And then we have some flows into the stock and out of the stock. The first flow is births, an inflow. And then we have an outflow of deaths and an outflow of migration. And then we have the stocks and the flows. So now we'll put in some parameters. And the first parameter we will put in is the birth rate. And then we'll put in the life expectancy. And we'll put in the fraction of people, of population migrating. And we'll put in the migration rate. And we'll put in the initial population. Okay, so now we're going to connect these parameters to the flows. So we will connect the birth rate to the births and the population to the births. We'll connect the life expectancy to the deaths and the population to the deaths. We'll connect the fraction of people migrating to the deaths because we assume that people will either migrate or they will die of old age. And then we'll connect the fraction of people migrating to migration, and we'll connect the life expectancy to migration. Because as I said, this is the migration of people over a lifetime. And we'll connect the initial population to the population, and we'll connect the migration rate to the fraction of people migrating, and we'll connect the life expectancy to the fraction of people migrating. And I'll show you why I've done these connections in a few minutes. So let's put formulas to these. So we will say that the births are the population times the birth rate. And the units here, it's very important to specify the units of your model. And we'll specify this as people per year. And then we'll specify the population. And you can see the population is equal to the births minus the deaths minus the migration. So we have the inflows and the outflows. And we specify the initial value as the initial population. And we will say that this is in units people. And then we have the deaths, and the deaths is equal to the population times 1 minus the fraction migrating divided by the life expectancy. So that is basically saying that the people who don't migrate will eventually die of old age. And then the migration rate, migrations is, I have to put the population into the migration rate. Okay, so the migrations is the population times the fraction of population migrating divided by life expectancy, and this is also in people per year. And the fraction of people migrating is equal to the migration rate times the life expectancy. And this is a dimensionless variable. It's a fraction. And the migration rate, we know by looking it up, is that the migration rate is 0.3 people per thousand per year. And so this is in people per year. And then we don't know the initial population, the birth rate, or the life expectancy yet, and we will have to calculate those. But let's put the units into them first before we move on and calculate the actual values for these parameters. So the first thing I'll do is I'll specify the birth rate units, and the birth rate units are people per year. And the population, initial population, is people, and the life expectancy is years. Okay, now Vensim has a very nice feature that you can check the units. So let's see if we have the units correct. You have to save the model first. So we'll save it as population, and we'll save it, and the units are okay. So now we have confidence that we have a good model. And now we're going to estimate the parameters that are missing. And I'll show you these, how I do this using calibration to data. So here I have data on the population of Nigeria from 1950 to 2021. And I'm going to build a model that's identical to the Vensim model, except it'll be in Excel. So the first thing I'm going to do is I'm going to specify the stock of the population, and I'm going to give that a value of the initial value in 1950. And then I'm going to specify the births, and I'm going to say that the birth rate, I'll start off with a birth rate of 0.02, and that's in people per year. And I'll set the births as equal to population times the birth rate. And I'll anchor the birth rate by putting a $sign between the letter and the number. So now I have the birth rate, and then I'll have the deaths. And I'll have the migration. And I'll specify here the migration rate. And I'll specify here the fraction of population migrating. And I'll have the life expectancy of the population here. So let's start with the value, as I said, of 0.3 people per thousand as the migration rate. And I'll set this life expectancy as 55. And I'll set the fraction of people migrating as the migration rate times the life expectancy. And that gives me this value here. So, sorry, this is 0.3, sorry. And so now we have the deaths is equal to the population times bracket 1 minus the fraction of the population migrating divided by the life expectancy. And I will anchor these values by putting a $sign between the letter and the number. And that'll give me the deaths. And now I have the migration rate, which is the population times the fraction of people migrating divided by the life expectancy. And I'll anchor these values. And this is now one last thing to do, and that is I have to specify the population in year 51. So the population in year 51 is equal to the population in year 50 plus the births minus the deaths minus the migration. And that's the new population. And then we can calculate the new births. And we can calculate the new deaths and the new migration. And now we can copy this down to 2021. Sorry. Okay, so now we have the model, and this is a model that's identical to the system dynamics model. And now I'm going to estimate the two parameters. I'm going to estimate the birth rate and the life expectancy. And I'm going to do that by minimizing the error between the actual value and the model value. So let me just first of all put the parameter here. I'll call it model population. And I'm going to make a graph of the actual population and the model population. And I have this model. Model population is not very close to the actual population with the parameters that I have in the model at present. So I want to get the model population to be a good match of the actual population. And I'm going to do that by minimizing the squared error between the actual value and the model value. So I take the actual value and I subtract the model value, and then I square it. And then I will cut and paste this down for all of the years in the model. And then I'll take the sum of all of those squared errors. And that gives me this number here, which is very large. And now what I'm going to do is I'm going to use a technique called solver. And solver, I'm going to use it to minimize this value here, the sum of squared error. And I'm going to do that by estimating the birth rate and the life expectancy. And I'm going to run this now. And when I look at the results, I see that I have a fairly good match between the model and the actual population. So now I can take this model, take these results from Excel and put them back in VinSim model. So let's go to the birth rate, and I will copy that, and I'll put it into the birth rate, and I will take the life expectancy. I'll copy that and put it into the life expectancy. And I'll take the initial population, and I'll copy that and put it into the initial population here. One thing I have to do is I have to remove the commas because VinSim doesn't like commas. So then I now have a model, and as you can see, all of the values are specified. And the last thing I'm going to do is I'm going to change the timeline. I'm going to say that the values will start in 1950, and I'm going to run it for 100 years until 2050. Okay, so now I can run the model, and I can look at the population, and I see that the population increases to about almost 450 million people by 2050, if nothing changes. So that's a very simple model, and I showed you how to calibrate it, and I showed you how to use VinSim and Excel together to build a realistic model. And now I'm going to do another model, but it'll be a demographic model. So I'll save this, and I will close it, and I'm going to open a model that I've built before on the demographics. And this model has children, adults, and elders as stocks. So it's a demographic model of the aging chain of people in the population. It has children dying and children migrating, adults dying, adults migrating, and elders migrating and elders dying. And it also has children maturing and adults maturing. And it's got two fractions. It's got the fraction of children migrating and the fraction of children dying. So when I go to run this model, I see that I have to estimate a number of these parameters that are undefined at present. So I'll go to, I have also developed an Excel spreadsheet for this. So let's go to the Excel spreadsheet. It's a little bigger. So here's the Excel spreadsheet, and we have here the actual elders in this column, the actual adults in this column, and the actual children in this column. And we have the squared error between the actual elders and the model elders. We have the squared error between the actual adults and the model adults. And we have the squared error of the actual children and the model children. And then we have the sum of the sums of squared error, the total sum of squared error is equal to these three values added together and into this parameter here. And we have the births, the deaths, the migrating, the maturing. So we have all the stocks and flows shown here. And we will do a solver. And we're going to modify the birth rate and the death fraction and the death fraction and the life expectancy. Okay, so now we've got the results. And if we look at the charts, we see that we have a little bit of a problem with the elders. So let's run the solver again. And now we see we have a good match between the elders, model elders and the actual elders, between the adults and the actual adults, and between the model children and the model adults. So now we'll bring these values back into the Vensim model. And so we will copy and paste this into the birth rate. And we'll cut and paste the fraction, the death fraction of children. So we'll copy that and put it in here. And we'll copy the death fraction here into here. And we'll copy the life expectancy here. Okay, so now we have a model and we can check the units. And the units are okay. And now we'll check the settings and we'll run it from 1950 to 2050. And when we run it, we can now look at the results. So if I go here and look at a graph, I can see that we have adults is the red line going up to 200, a little over 200 million in 2050. And children is the blue line, which is going to go almost to 200 million by 2050. And the elders is quite low. So this is an interesting demographic that the number of children between 0 and 15 will almost be equal to the number of adults in the population. So this will be an interesting demographic for a challenge for Nigeria over the next 30 years. And we can discuss that challenge in the question and answers. So that's my presentation on the building blocks of system dynamics. And I'll open the floor to questions now.